Fantastic. All right, so we're looking at derivatives as a rate of change, which, should not be new to us at all. And what we're going to do is we're going to determine the extreme values on this, which means we need to check what? What are the two things? No.
Zeros?
I guess technically we need to check continuity, but it's a polynomial, so it's continuous. Zeros and endpoints. Okay, so first thing I'm going to do is I'm going to take the derivative. It's going to be 3x squared minus 6x. I'm going to make it equal to 0. And I'm going to pull out my common factor. Therefore, my zeros are x equals 0 and 2. So then I check my endpoint, f of -1, f of 0, f of 2, and f of 3. And I'm looking for what my absolute max, my absolute min are, right? So if I plug in -1 up here, I'm going to get -1 minus 3, that's -4. If I plug in 0, I get 0. If I plug in 2, I'm going to get 8 minus 12, which is -4. And if I plug in 3, I'm going to get 27 minus 27, which is 0. Therefore, the zeros would be my ab max. They are the biggest number. And the -4s would be my ab min. Is it normal, or is this a little bit strange that every single one of them was a max and min?
It's weird.
It's a little weird, right? But it can happen. But typically we just get one ab max or ab min, but occasionally, yes, we can get more than one. All right, let's jump into what we're doing for real now. So, derivative as a rate of change, which means we're going to talk about the mean value theorem, and we're going to talk about Rolle's theorem. So, consider the values of a differentiable function f of x in the table below to answer the questions that follow, and plot the points and connect them on the grid below. All right, so, well, we got to just plot the points. So, 0 and 1. And then 2 and 5. And then 4 and 8. 6 and 10. 8 and 11. 10 and 10. 12 and 8. 14 and 5. 16 and 1. What does that make? What shape is that? That's not a triangle. It's a parabola. Do your best to sketch that in. Do your best. Excellent. All right. We drew in the points. We connected them. We rock. All right. So calculus derivative, we got a bunch of different interpretations, which we've talked about. One of the most important interpretations that the derivative represents the rate of change of a function. This is the one we talk about all the time. Okay. If we're talking about the rate of change, there's two rates of change that can be found with an associated function. The average rate of change, which is what kind of line? Do you remember? We got two kinds of lines, secant and we got tangent. Which one is the average? Secant. The tangent line is the instantaneous rate of change, right? It's what is the rate of change at that instant, okay? All right. Average rate of change of f of x on an interval. So, like I said, this is our secant line. All right, so this means that on the interval, a and b, the average rate of change, which I believe we started calling rocks earlier, can be found. And this is literally just finding the slope the way you've been finding the slope for years, right? So it's just going to be like f of a minus f of b over a minus b. Could I switch a and b? Would it be the same thing? Absolutely. I'm seeing quite a few of you nod. Excellent. Yes, it would just switch them. It's not a big deal. F of b minus f of a over b minus a gives us the same thing. All right. Then the instantaneous rate of change, which we talked about. Oh, I thought I had fixed my pen. Why is it doing that? Again. Okay, this is the tangent line. And I guess technically we should be a little more specific. It's the slope of these things. Right? So the instantaneous rate of change is at a value x equals a. The instantaneous rate of change. Oh my gosh. I don't know why this thing is messing up so bad lately. It's going to be painful. Is found by f prime of a. This might be a long lesson if my pen keeps doing it. I thought I had fixed it in the last class, but now it seems to not be working again. We'll see. Okay. So then, find the average rate of change of f of x on the interval 2 and 12. Well, first of all, let's go up and actually draw what that might look like, right? So from 2 here until 12. And so that should look like that, which of course is our secant line, which means it is our average. Okay, how do we do that? Well, we just take those 2 points and we subtract them, right? We just literally do our rise over run. So it's going to be f of 2 minus f of 12 over 2 minus 12. F of 2 is 5, f of 12 is 8. So we're going to get 5 minus 8 over negative 10, which gives us negative 3 over negative 10, but the negatives then would cancel. So I would just get 3/10. Easy enough? Makes sense? Anybody lost? Feel good about that? Bartuz, you good? Matthias, you good? All right. Now let's find the instantaneous rate of change. So I'll maybe do that one. We'll just switch back to blue, I guess. At x equals 4. Oh, no, sorry. They want to know, is the one at 4 greater than the one at 6? Justify our answers. All right, well, let's go up here. At 4, I'm going to need something that looks like that. And at 6, something that looks like that, right? Those would be my 2 tangent lines. Which one of those tangent lines is steeper? 4. Does that mean that that one's going to be bigger or smaller? Bigger, right? Steeper means bigger, exactly. So, is the instantaneous rate of change at 4 greater than that at 6? Yes, it is. So we can say that f prime of 4 is greater than f prime of 6 because the slope of the tangent line at x equals 4 is bigger than that of x equals 6. Amazing, right? Not hard, hopefully. Hopefully. Now, if you couldn't draw the tangent line, what could you do instead to figure that out? Take the derivative and just plug in 4 and 6, right? And see which one's bigger. And if you plug in 4, you're going to get a bigger number. Absolutely. All right, let's talk about Rolle's theorem. Oh, you need a second. Okay. Talk about Rolle's theorem, which is really just a fancy, that's just a fancy form of another theorem we already know. Okay, we're good. All right, so for Rolle's theorem. All right. If f of x is continuous, because that's kind of like our standard, that's got to be true, right? On a, b, closed interval, and if it's differentiable on, do I include a and b this time? Can you differentiate an endpoint? No, so it's just going to be on ab, right? Parentheses rather than brackets because we don't include it. And if f of a is equal to f of b, then there, before we even go further, what does f of a equals f of b mean? The same height. Exactly, right? So like the y coordinate's going to be the same. Then there is guaranteed to exist a value of, we'll call it c, on that same interval of AB, such that f prime of c equals 0. What does that really mean?
That there is like a maximum.
Exactly. If we have two endpoints that are the same, then we know that inside of there has to be a max or a min. There has to be a critical point, right? Now, you might say, well, what if it's a straight line? Well, then guess what? The whole thing is the max or the min, right? Like if it's just a straight line across between them, okay? Like if you just have a straight line, like if they're at the exact same height, well, then the whole thing is your max or min. But what we're saying is usually you're going to get something like this, right? Where you're going to have at least one value that is a max or min. And this is the only case that you would see to try and like disprove that, but this would just mean the whole thing is the max or the min. All right?
When you say such that f prime of c equals 0.
Because that would mean that the derivative equals 0. So the derivative is a critical point. Or because the derivative equals 0, it means it's a critical point. Right? So it's a max or min. Yes? Yes. Perfect. Okay. So we're going to consider the function f of x presented on the previous page. I don't remember what it is. This one here. Okay. So on the interval from 2 to 14. Okay. Well, what we need to do then is in order for this rule to apply, what has to be true? It has to be continuous, which it is. It is differentiable. So what's the last step that needs to be true? It means that you can take the derivative. F of a equals f of b. So we need to know, does f of 2 equal f of 14? So if you scroll up there and look, right, f of 2 is 5, f of 14 is 5. So in both cases here, this is equal to 5. So therefore, does Rolle's theorem apply? Yes. And our reasoning is simply because the endpoints are the same, and f of x, technically we gotta say like an f of x is continuous and differentiable. Now, we already know that because it told us that at the beginning, so we won't write that part again on the next one here. The only part that we're going to have to prove once we've said, hey, yeah, it's continuous and differentiable is, are the two things the same? So for 2 and 10, it's going to be yes or no because, like I said, we always start with justification. It makes our life easier. We know what we're looking for. We need to know, does f of 2 equal f of 10? No, it does not, right? Because f of 2 is 5. What is f of 10? Those things aren't equal, so we say no. We cannot use Rolle's theorem. Easy enough, yeah? Yep.
Like I said, like you said, even if you can't apply it, it can still be a match for me.
Yeah. Yeah. Basically, all of these theorems, you guys, just are like shortcuts to be like, hey, yes, we can do this, so let's actually, it's worth investigating. If you can't use the theorem, it doesn't guarantee there isn't one. It just means that it doesn't guarantee that there is one. So what the theorems do is help us say, hey, do some more work. Because most of the time, like the theorems, you can figure it out real quick just by kind of looking or by doing some quick math, and so that's why. All right, let's keep it moving. All right, so then for each of these functions, we're going to see, can we apply Rolle's theorem? And if we can, use it, okay? If not, stay why. Okay, so here, is this function continuous? Is it differentiable? Yes, right? It's a polynomial. We love polynomials because they're super easy. They work for everything. That's why we always learn about them first. Okay? So that means that all I need to do then is prove the third part, which is, does g of -3 equal g of 0? We want to know, is that true? Well, that means we got to just plug them in. 0's easy. What's g of 0? 0. Perfect. All right. So then all I got to do is plug in -3. -3 squared is 9 times 9 is 81. -3 to the power of 4 is also 81. So 81 minus 81 is 0. Checks out. We can use it. Okay. So that means then that we should take the derivative. So g prime of x is going to be 18x minus 4x cubed. Then, if I'm trying to find the critical point, right, I'm going to want to make sure that I factor this out. And I'm going to make it equal to 0. So here I can take out a 2x, looks like, which would give me a 9 minus 2x squared. All right. This one here is 0. Okay. Can I include 0? No, because it's the endpoint. And remember, the relative max or mins cannot be an endpoint, right? The absolutes can, but the other ones cannot. All right, then this one I got to actually solve. So this is going to be like 9 equals 2x squared. And then I would divide by 2. So I'd get like, and then square root it. So the square root of x squared is going to be equal to 3 over square root 2. Or just x equals 3 over square root 2. Why? Because I applied the square root to the 9, because I might as well, right? Square root of 9 is 3. So I get this. Technically, I suppose I shouldn't be saying, whoa, that was kind of fun. I shouldn't be saying it's x, actually, should I? Because we technically said it was c. So we should be pretending it's c, right? We're trying to figure out if that exists. All right. And when we take the square root of something, what else do we have to remember?
What?
Square roots are always plus or minus, right? Does positive 3 over root 2 fit within our domain?
Yes.
No. So therefore we get c equals -3 over root 2, which is less than -3. Or if you prefer, I suppose you could write that one still as like, or -√9 over 2, if you'd rather leave it that way, okay? But yeah, that would be what it is. Amazing. So basically, what did we learn? Just that Rolle's theorem told us, hey, go ahead and look for one because there should be one, right? That's all it was. Okay, let's try the next one. Here we got g of x. Is it continuous?
No.
No, it's discontinuous where? Is -2 on our interval? Yes. Therefore, we cannot use it. So no. G of x is undefined. Undefined at x equals -2, which is on our interval. So therefore, no Rolle's. Rolle's theorem guarantees nothing. Does that mean there isn't one? No. Just means it can't guarantee it. So. What's up? Yeah, go. You should fill out your pass since you guys got mad at me for. Rolle's theorem guarantees that if a function is continuous on a closed interval AB, differentiable on the open interval AB, and f of a equals f of b, then there's guaranteed to exist that 0, or that value c, which would be an x, on that interval where the instantaneous rate of change is 0. In other words, it guarantees us a critical point. That's all it's saying, right? All right, perfect. So before we start mean value theorem, let's do a stretch break. Well, after the worst stretch break in history, we will continue. Manuel, you can leave. Because you came in late, you don't have your stuff out, and now you're talking what we're trying to teach. No, dude, come on, get your foot down and do the work. Okay, mean value theorem is very similar. In fact, Rolle's theorem is actually just a special case of mean value theorem. So, what is mean value theorem then? Let's write it down. So, if f of x is continuous, because it's calculus, and that always has to be true, on our interval AB. And remember, for continuity, we include those endpoints. And if it's differentiable on the open interval AB, because we can't differentiate an endpoint, then there is guaranteed to exist a value of C on that same open interval such that, and here I'm going to like leave a space to write it down for myself, and this means that the instantaneous rate of change will be equal to the average rate of change somewhere. Now, you might be like, what? I need the formula. I don't understand. You're correct. So let's write that formula. I got you. All right. So what it's saying is that f prime of that value C is going to be equal to f of A minus f of B over A minus B. And so then this is kind of that key thing. What it means is that our instantaneous rate of change, at some point, the average rate of change and the instantaneous are equal. They have to be. They have to be equal somewhere. And that's why with Rolle's theorem, if we have the two endpoints are the same, what's the rate of change? The average. 0, right? Because if they're both the same, hey man, we said no stretch break. It's fine, I'm kidding, you can stretch. Okay, so that means then that the instantaneous rate of change has to be 0 somewhere, and an instantaneous rate of change of 0 means critical point. Okay? So that's why Rolle's theorem is just a special case of mean value theorem. Rolle's just wanted his name on something. You don't understand anything. Really? That's unfortunate for you. Why do you think that is?
Let me start. I understand that maybe you can explain better, like show me like a little graph.
Well, that's what I'm doing. That's what I'm doing. That's literally the next thing we're going to do, man. Consider the function h of x equals 3 minus 5 over x, which is shown below. The graph of it is pictured. Does the MVT apply on the interval from -1 to 5? Explain why or why not. Heck no. From -1 over here to 5? Does the function exist over here? No. So we say no, because h of x, we do know, is not continuous. And why is it not continuous? Where does it not exist, guys? No. Look at the equation. Come on. Where is it not continuous? At x equals 0, right? I can't divide by 0. Okay? All right, so it's not continuous at 0, so can't do it. Nope, forget it. Does it apply on the interval from 1 to 5? Heck yeah. Right, now I'm going from like here to here. Yeah, that works. I can do that. So yes, I guess we should say f of x, or h of x, sorry. H of x is differentiable. Now, do I technically need to say continuous then? No, because differentiable means continuous. Continuous doesn't mean differentiable, but differentiable means continuous. So we could say that, right? And we know that because it has none of those like hard corner cusps or whatever, right? So that's how we know, yeah, this thing is differentiable. Awesome. All right. So since it guarantees it, draw it on the graph to the left. Awesome. Okay, well, let's go from 1, which is here, to 5, which is here. So that means that's my average one, so not quite right there. If you have a ruler, it'll be easier for you. There we go. So that's my average, right? My secant line. And if you imagine this, and again, this is way easier if you have a ruler, because what you're going to do is you're literally going to keep the ruler in the exact same line, and you're just going to slide it out until it becomes a tangent line. Okay? So, if you have a ruler, which I'll show you right now real quick. Sorry for those who watching at home, you won't be able to see. But if I take my ruler and I line it up like this, right? And then I keep it in that exact same position, and all I do is I slide it out. You see how now, hey, there's my instantaneous rate of change, wherever the last place it touches the graph. So the average has to equal the instantaneous somewhere. Does that make more sense now, Pablo?
Yes.
Perfect. All right, so what does this mean? That we're going to have scribbles everywhere because my thing's breaking. Come on, man. Why does it hate me? It really hates me lately. All right. So, and this one is our instantaneous. So that's the instant. Does MVT guarantee things? Yes, it does. MVT guarantees that there exists there exists an f prime of c is equal to f of 1 minus f of 5 over 1 minus 5. Okay, guarantees that that's going to exist. Very next thing we're going to do is like figure out where is that. All right, so we're going to figure that out. So let's start by rewriting my equation. So h of x, instead of writing it as 3 minus 5 over x, we're going to make it easier on ourselves, right, and put that back up on top, that x, so it's cross the line, flip the sign, x to the negative 1. Now I can take the derivative nice and easily, so h prime of x is going to be equal to 5x to the negative 2. Or, like, over x squared. So I could say, like, h prime of c is going to be equal to 5 over c squared. So basically, what did we do? We said, well, like, that's the equation. That equation now needs to be equal to the average, which I can calculate, right? So what I'm going to do is I'm going to say, well, 5 over c squared has to be equal to f of 1. Actually, you know what? We don't need to write the actual definition again. I think we can just do it. So at f of 1, we get negative 2. At f of 5, we get 2. And it's over 1 minus 5. Now, just to kind of show you how this all coincides here. This is that f prime of c part, and the average is this part. And we're saying those two things have to be equal. Okay? So, that means that we're going to get 5 over c squared is equal to negative 4 over negative 4, which is just exactly. Then I solve for c, so I'm going to get 5 is equal to c squared. What's my last step? Square root it. And so I'm going to get that c is equal to plus or minus the square root of 5. Which one do I not care about? This one is outside the domain. Make sense? So we don't include it. It is outside. I guess maybe I should say outside the interval rather than domain. I mean, technically means the same, but interval is a better word. So let's use that. Outside my interval. And so finally, that means that c is equal to the square root of 5. Amazing. Good? 2 of you get it. The rest of you, good luck. No, you're just not paying attention. It's all good. All right. So let's continue. Explain why we cannot apply the mean value theorem on this equation on the interval from negative 1 to 1. Well, probably what's going to be a little bit easier is if we kind of rewrite this a little bit. And so if we go with, actually we can leave it like that for now, but we can take the derivative, which would be what? 2/3 x to the negative 1/3, or 2 over 3 cubed root x.
Why did you do that? Oh, no.
Because what, okay, why did I do that? Good question. Good question. What are the things that have to be true to use mean value theorem?
Differentiability, continuity.
And that's it, actually.
Elements have to be.
No, that's for rolls. So for this one, we just have 2. Okay? So if I look at it, it's a polynomial-like thing, 2/3, like x to the 2. All right, sorry, the video cut out there, but we said, yeah, it's a polynomial-like function, which meant that it was continuous. In order to figure out if it's defined, we had to take the derivative. And then we realized, hey, it's discontinuous at 0, which is on our interval. So because it is undefined at x equals 0, we cannot use MBT, right? It's not differentiable on our interval. Becomes a problem. Does that make sense to everybody? Yeah? We think so? Miguel thinks so? Excellent. All right, so now what we're going to do is we're going to find the equation of the tangent line to this graph on that interval at the point which is guaranteed by the mean value theorem. Okay, so it's telling us already that we can use mean value theorem, so we don't really need to check anything. But even if we did quickly take the derivative here, which actually is the first thing we got to do anyway. So f prime of x, right, is going to be 2 plus cosine of x. This is not written very well. This should be like that. It's not x plus 1 inside. Okay. And if you look at that, is that thing continuous everywhere? Yes. Is it differentiable everywhere? Yes, right? It's just a curve. It's a wave function. All right. So that means we can definitely use it. So now let's go ahead and let's apply that. So f prime of c is going to be equal to 2 plus the cosine of, oh my goodness, why? Driving me insane. Cosine of c, there we go. All right, so, and we know that that thing has to be equal to the average, right? So we know that this one is going to be equal to, our interval is from 0 to pi over 0 minus pi, because that's our average, right? All right, so then we get that 2 plus the cosine of c is equal to, what's f of 0 if I plug in 0 here? Well, that's easy, but what's sine of 0? What is the sine of 0? 0. Ah, it's 0. So it's 0 plus 0, so that's just 0 on top. At that point, does it matter what's going to be on the bottom? Ouch. Oh, no, wait, sorry. Yes, it does. Ow. So now, when I plug in pi, right, when I plug in pi, I'm going to get 2 pi plus what's sine of pi? 0. Yep. Oh, my goodness. Plus what? Ooh, actually, I messed that up then. Because when I plugged in 0, it is not 0. It's actually 1. Because it's 0 plus 0 plus 1. Yeah, my bad. Sorry. All right, and then it's over negative pi. All right, well, it's kind of ugly, but, you know, we can work that out. We can deal with that. So the nice thing is here, what happens to these 1s?
Cancel out.
Exactly. Right? 1 minus 1 goes away, so we're going to get negative 2 pi over negative pi, which means my negatives cancel, my pi's cancel, my pen stops working again. And so I get 2 plus the cosine of c is going to be just equal to 2. Well, that's looking good, because now when I subtract 2, I'm going to get the cosine of c is equal to 0. When does that happen? When is cosine equal to 0?
Pi over 2 and 3 pi over 2.
Exactly. Pi over 2 and 3 pi over 2. Now, once we get an answer, we should probably make sure those are both on our domain, right? So if I scroll up here, I'm going from 0 to pi. So which one do I need to get rid of?
3 pi over 2.
Exactly. This guy is outside our interval. So we're not going to include that one. So that means that this is our value. So now we can go ahead and find that tangent line. So our pot is going to be pi over 2, and I just plug pi over 2 into the original equation, right? Dear God, man. All right, which is going to be 2 pi over 2. I really cannot write right now. It's driving me nuts. Seriously, stop scribbling. I don't know what's going on. Okay. And then what's sine of pi over 2?
1.
1. And plus 1 again. So really our pot is going to be pi over 2 and pi plus 2. Right? Because there's a plus 1 in the equation, so it's still there. Right? The 2x, well, 2 times pi over 2 is just pi.
Why?
Because it's in the original, because that's our pot. That's our x value. So we have to plug the x in to get y. Yep. Yep. All right, so then I need my SOT. So I'm going to plug this into my derivative now, which is the 2 plus cosine. So cosine of pi over 2 is 0. So it's just 2 plus 0. Beautiful, it's 2. Which means that it's just going to be y minus pi minus 2. Or if you prefer, y minus pi plus 2. Whichever way you want to write it. Equals 2 times x minus the x coordinate, pi over 2. And so that is our equation. Amazing, right? So just to reiterate, our mean value theorem guarantees that if a function is continuous on the closed interval, AB, and it's differentiable on AB, open, then it's guaranteed to exist a value of c where the instantaneous rate of change is equal to the average rate of change. So our secant line slope is equal to the tangent line slope, in other words. That will always be the case. And that's it, guys.